Have you ever looked up at the night sky and wondered about the stars? The ancient Greeks did too. They were some of the first to try and understand the world around them using reason and observation. These early thinkers, like Aristotle, didn't always get everything right, but they laid the groundwork for the science of physics. Aristotle believed that everything in the universe was made of four elements: earth, air, fire, and water. He also thought that objects moved because they had a natural tendency to seek their natural place. For example, a rock falls to the ground because it's made mostly of earth. Another important Greek thinker was Archimedes. He discovered the principle of buoyancy, which explains why ships float. Archimedes also invented many machines like the screw pump, which is still used today. The ancient Greeks left us with a legacy of curiosity and a desire to understand the natural world. Their ideas, though not always correct, paved the way for the scientific revolution that would transform our understanding of physics. Centuries after the ancient Greeks, a new era of scientific discovery emerged in Europe, the Renaissance. During this time, thinkers began to challenge the old ideas and develop new ways of understanding the universe. One of the most important figures of the Renaissance was Nicholas Copernicus. He proposed a revolutionary idea that the Earth and other planets revolve around the Sun. This contradicted the long-held belief that the Earth was the center of the universe. Galileo Galilei was another key figure in this scientific revolution. He made significant improvements to the telescope and used it to make groundbreaking observations of the moon, planets, and stars. Galileo's work provided further evidence for Copernicus's heliocentric model of the solar system. The Renaissance marked a turning point in the history of science. It was a time of great intellectual curiosity and a willingness to challenge established ideas. This new way of thinking paved the way for the scientific breakthroughs of the 17th century. Imagine a world without cars, airplanes, or even buildings. That's a world without Isaac Newton. This brilliant scientist developed the laws of motion and gravity, which explain how objects move and interact with each other. Newton's first law of motion states that an object at rest will stay at rest and an object in motion will stay in motion at the same speed and direction unless acted upon by an unbalanced force. This is also known as the law of inertia. His second law of motion explains how force, mass, and acceleration are related. It states that the acceleration of an object is directly proportional to the force applied to it and inversely proportional to its mass. Newton's third law of motion states that for every action, there is an equal and opposite reaction. This means that when you push on an object, the object pushes back on you with an equal force. Newton's law of universal gravitation explains why objects fall to the ground and why planets orbit the sun. It states that every object in the universe attracts every other object with a force that is proportional to their masses and inversely proportional to the square of the distance between them. Have you ever rubbed a balloon on your hair and watched it stick to the wall? That's static electricity in action. For centuries, electricity and magnetism were considered mysterious and unrelated forces. But in the 19th century, scientists began to unravel their secrets. Benjamin Franklin famously demonstrated the connection between lightning and electricity with his kite experiment. He also introduced the concepts of positive and negative charges. Alessandro Volta invented the first electric battery, the voltaic pile. This invention allowed scientists to study electricity in a more controlled way. Hans Christian Ørsted discovered that electric currents create magnetic fields. This was a major breakthrough in understanding the relationship between electricity and magnetism. Michael Faraday discovered electromagnetic induction, the principle behind electric generators and transformers. He showed that a changing magnetic field could induce an electric current in a nearby wire. These discoveries paved the way for the development of electric power, which would revolutionize the world. Section 5. James Clerk Maxwell, the Great Unifier. In the 19th century, James Clerk Maxwell developed a set of equations that unified electricity, magnetism, and optics into a single theory, electromagnetism. Maxwell's equations are considered one of the greatest achievements in physics. These equations describe how electric and magnetic fields are generated and how they interact with each other. They also predict the existence of electromagnetic waves, which travel at the speed of light. Maxwell's work showed that light is an electromagnetic wave, and it unified the previously separate fields of electricity, magnetism, and optics. His equations laid the foundation for the development of radio, television, and other wireless technologies. Section 6. Albert Einstein, Revolutionizing Physics. Albert Einstein is perhaps the most famous physicist of all time. His theories of special and general relativity revolutionized our understanding of space-time, gravity, and the universe. Einstein's theory of special relativity, published in 1905, states that the laws of physics are the same for all observers in uniform motion. It also shows that time and space are not absolute, but are relative to the observer's motion. One of the most famous consequences of special relativity is the equation E equals mc squared, which shows that energy and mass are equivalent and interchangeable. Einstein's theory of general relativity, published in 1915, extends special relativity to include gravity. It describes gravity not as a force, but as a curvature of space-time caused by the presence of mass and energy. Einstein's theories of relativity had a profound impact on physics and our understanding of the universe. They have been confirmed by numerous experiments and observations and remain cornerstones of modern physics. Section 7. Quantum Mechanics, the strange world of the very small. In the early 20th century, physicists developed a new theory to describe the behavior of matter at the atomic and subatomic levels, quantum mechanics. This theory revealed a strange and counterintuitive world, where energy and matter can behave like both particles and waves. One of the key figures in the development of quantum mechanics was Max Planck. He proposed that energy is quantized, meaning it exists in discrete packets called quanta. This idea revolutionized our understanding of light and energy. Niels Bohr developed a model of the atom in which electrons orbit the nucleus in specific energy levels. This model explained the spectrum of light emitted by atoms. Werner Heisenberg formulated the uncertainty principle, which states that it is impossible to simultaneously know both the position and momentum of a particle with perfect accuracy. Quantum mechanics has had a profound impact on technology, leading to the development of transistors, lasers, and other important inventions. Section 8. The Expanding Universe, from the Big Bang to Dark Matter. In the 20th century, astronomers made groundbreaking discoveries that revolutionized our understanding of the universe. Edwin Hubble observed that galaxies are moving away from us, providing evidence that the universe is expanding. This discovery led to the development of the Big Bang theory, which states that the universe originated from an extremely hot and dense state about 13.8 billion years ago. The theory explains the observed expansion of the universe and the cosmic microwave background radiation, which is thought to be a remnant of the Big Bang. Further observations revealed that the expansion of the universe is accelerating. This discovery led to the concept of dark energy, a mysterious form of energy that is thought to be responsible for the acceleration. Scientists also discovered that there is more matter in the universe than we can see, called dark matter. Although we can't observe dark matter directly, its gravitational effects on visible matter provide evidence for its existence. These discoveries have opened up new frontiers in physics and cosmology, leading to ongoing research into the nature of dark matter, dark energy, and the early universe. Section 9. Physics and the Future, Endless Possibilities. Physics is a constantly evolving field, and new discoveries are being made all the time. From the search for new particles at the Large Hadron Collider to the development of quantum computers, physics continues to push the boundaries of our understanding of the universe. One area of active research is the development of new energy sources. As we face the challenges of climate change, physicists are working to develop cleaner and more sustainable energy technologies such as fusion power and advanced solar cells. Another exciting area of research is quantum computing. Quantum computers have the potential to revolutionize fields such as medicine, materials science, and artificial intelligence by solving problems that are intractable for classical computers. Physics plays a vital role in our understanding of the world around us. From the smallest subatomic particles to the largest structures in the universe, physics seeks to explain the fundamental laws that govern our reality. As we continue to explore the mysteries of the universe, physics will undoubtedly continue to shape our understanding of the world and drive technological innovation for generations to come.